Okay, let's unpack this.
Let's do it.
We have a genuinely monumental piece of work in front of us today, introducing VL-JEPA, Joint Embedding Predictive Architecture for Vision Language.
Indeed. And our mission here is to really execute a deep dive into this paper. We want to give you a professional, comprehensive overview of its core technical contributions.
Right. We're focusing entirely on the novelty of the architecture and, of course, the quantitative results.
And just to be clear, for our audience, you're all operating at an expert level in ML and data science. We're skipping the basics. We're jumping straight into the implications of this, well, this paradigm shift.
Exactly. This isn't just another incremental VLM paper. I mean, this fundamentally challenges the established autoregressive paradigm.
It really does.
So before we get into the architecture itself, I think we need to clearly define the twin inefficiencies of classical, token generative vision language models that VL-JEPA is aiming to fix.
The first, and I think you'd agree, maybe the most expensive problem is the inherent inefficiency in the training objective itself. Standard VLMs are token generative. That means that they're using a maximum likelihood objective to predict the next discrete token in, say, a target sequence Y.
Which forces the model to learn to model the entire textual response distribution.
The entire thing. And that distribution is incredibly noisy.
So why is it so noisy? What's in there?
Because it's capturing two things at the same time. You have the task-relevant semantics, the core information you actually want, and then you have all this task-irrelevant surface linguistic fluff.
Like stylistic choices, specific word variations, syntax.
All of it. I mean, think about it. If you ask a VLM to describe a dog jumping over a fence, you could get the brown dog leaps the wooden barrier, or a canine is jumping above the fence.
Semantically, those are identical.
Exactly. But in the raw token space, the model sees them as highly distinct, maybe even orthogonal targets. So it has to dedicate just this massive amount of computational effort to resolve the differences between all these valid, equally correct surface forms.
That's a perfect analogy. It's like training the system not just to recognize a plate of food, but also to perfectly replicate the handwriting font that's used on the menu.
Precisely. And then there's the second inefficiency, which is crippling for any real-time application, in inference latency.
Right. The autoregressive token-by-token decoding.
Because they decode token by token, you have to wait for the entire, or at least a big chunk of the output sequence to generate before you get the core message.
And that high latency is just a non-starter for low-latency streaming applications, like live-action tracking in video.
It is. And critically, it completely prevents things like sparse or selective decoding. You're stuck generating everything.
And this is the conceptual pivot. This is what VL-JEPA delivers. It shifts the learning paradigm entirely away from token generation.
It is the first non-generative model built for these general domain vision language tasks that's built on the JEPA structure. The core innovation here is that it predicts a continuous embedding SY in a highly abstract latent space.
Instead of predicting discrete tokens Y in that noisy data space.
So you're learning the semantics directly in a really compact space, and you get to bypass all that explicit modeling of grammar and style during the heavy training phase.
And the high-level numbers, the quantitative contributions, they really reflect this efficiency gain.
They absolutely do. In controlled comparisons, VL-JEPA achieved superior performance. And it did this while using roughly 50% fewer trainable parameters in the prediction component compared to its token generative baseline.
And on top of that, it natively supports selective decoding, which empirically yields, a nearly threefold reduction in decoding operations.
An impressive reduction, yeah. Almost 3 times. It's a huge gain for streaming benchmarks.
Okay, let's pull back the curtain on how they engineered this. We need to walk through the components of this joint embedding predictive architecture. It feels very modular, very purpose-built.
It absolutely is. The architecture is modular and really optimized. It's defined by 4 core components. First, you've got the X encoder.
Okay, so that's mapping XV to SV.
Right. It takes the visual input, an image or video frames, and it maps it to these compact visual embeddings, SV. You can think of them as analogous to visual tokens, but really optimized for what comes next.
And in this specific implementation, they anchored this visual foundation with a frozen VJPay to VPI-TL, a really solid choice to ensure robust visual representation from the get-go.
Yes, that's a key decision. It lets them isolate the vision language learning challenge.
Yeah.
Then the second component is the Y encoder.
Y to SY. This is the semantic gatekeeper, right?
That's a great way to put it. It embeds the textual target, Y, into that continuous latent space. And crucially, the Y encoder's job is to just throw away all that task-irrelevant surface information.
So it's focusing the resulting embedding, SY, purely on the semantics.
Purely. And this module is absolutely vital because if the Y encoder fails to abstract away those surface features, well, the entire efficiency benefit is lost.
Then comes the predictor.
The predictor is the core engine here. It's learning the conditional mapping. It takes the visual embeddings, SV, maybe conditioned by a textual query, XQ, for VQA tasks, and then it outputs the prediction of the target embedding, which is SY hat.
So this is the component that's learning that complex alignment between vision and language semantics.
This is where the magic happens. And the final piece is the Y decoder.
And this is the part that, only exists when we actually need human-readable output, right?
Precisely. It's lightweight. It's only active at inference time. It just translates that predicted semantic embedding, SY hat, into human-readable text. Its exclusion from the main training loop is fundamental to the whole efficiency profile.
Okay, so if the conventional VLM objective is, the distance between the generated text and the true text.
LVLM equals DY hat Y.
Right. Then VL-JEPA optimizes LVL-JEPA equals DSY hat SY, the distance between the embeddings. Which brings us back to the core concept. Why is operating in this continuous embedding space so dramatically more efficient?
It solves that semantic problem that's just inherent in these ill-posed tasks. The multiple valid answers we just talked about.
Mm-hmm.
So imagine a trading example where you have correct descriptive captions for an image, but they're all syntactically diverse.
Mm-hmm.
In the raw token space, the probability distributions for those targets are just spread all over the place.
From a modeling perspective, they're basically orthogonal.
They are.
Oh.
And this results in a sparse, high-dimensional, multimodal target distribution that is incredibly challenging for any model to learn efficiently.
It's like trying to hit 3 separate tiny targets simultaneously with one shot.
Exactly. And the beauty of the Y encoder is that it maps those semantically similar but syntactically distinct captions to points that are clustered very closely together in the latent space.
So it simplifies the target distribution.
It simplifies it into a compact, robustly unimodal one. The model is no longer forced to learn every single permutation of valid sentences. It only needs to learn the single, central semantic concept.
That makes perfect sense. Simpler target, faster learning. So given that, what's the specific optimization strategy? What loss function are they using to enforce this alignment?
The authors use the bidirectional info and CP loss. They chose it because it's proven to be really effective at balancing alignment and discrimination in multimodal learning.
Okay.
Mathematically, it works by separating the learning goal into 2 components. First, there's the representation alignment term, which minimizes the distance between the normalized prediction SY hat and the true target SY.
That's the core prediction engine.
Right. And second, it includes a crucial uniformity regularization term. This is what prevents representation collapse.
Okay.
It forces the embeddings within a batch to stay sufficiently far apart, ensuring that the latent space maintains high discriminative power. It has to be able to distinguish between different semantics, not just collapse everything into one region.
Okay, that gives us the theoretical framework and the loss function. And this is where it gets really interesting for me. Let's transition from the theory to the actual implementation.
Yeah.
How did they build this thing? Which foundational models did they leverage?
This is where you see that pragmatic engineering meeting the architectural innovation. They constructed a 1.6 billion parameter model. As you already noted, the X encoder was that frozen VJB2 VITL.
Right.
For the Y encoder, the module responsible for generating those crucial semantic text embeddings, they initialized it with embedding Gemma 300 meal.
A great choice for embedding quality and efficiency. But what about the predictor, the component doing the heavy lifting of that conditional mapping?
The predictor, which has 490 million trainable parameters, was initialized using the last 8 transformer layers of Llama 3.2.1b.
Now, that's a very calculated decision.
It is. By leveraging the upper layers of a pre-trained LLM, they're essentially bootstrapping the predictor with robust, pre-learned mechanisms for future transformation and context integration. It's ideal for a mapping function.
So that's a highly pragmatic way to bootstrap the model. But does mixing components from different families, Llama and Gemma, introduce any instability or friction? Or is it pretty straightforward because the loss is all in that shared latent space?
It's straightforward precisely for that reason. The loss is contained in the shared latent space, which they set to 1,536 dimensions. Their only real training tweak was applying a small learning rate multiplier times 0.05 to the Y encoder parameters early on.
So what does that suggest?
It suggests they needed to just gently guide the Y encoder to align optimally with the predictor's output distribution, but overall the method proved to be highly stable.
Let's detail the training strategy then. We have two distinct stages here.
Stage 1 is the large-scale pre-training. This creates what they call the VL-JEPA base model, and this is purely focused on establishing a robust vision-language alignment in a query-free way. They used massive, noisy datasets like PLM Image Video Auto, YFCC100M, and they even included an image-only phase where the model saw 2 billion samples, followed by a joint image video pre-training. This stage really builds the foundation.
And stage 2, supervised fine-tuning, or SFT, is where they tailor the model for real-world question answering.
Correct. SFT is the query condition stage. They use millions of VQA, captioning, and classification samples. This creates the VL-JEPA SFT model, optimizing its ability to handle complex task-specific queries while preserving that alignment it gained in stage 1.
What I find most impressive here is how this single architecture leverages that predicted embedding, SY hat, to perform fundamentally different tasks generation, classification, retrieval, without needing specific architectural changes.
That's the power of latent-based prediction. For generation tasks like open-ended VQA, it's simple. Predict SY hat, run it through the lightweight Y decoder, and you get your text. But for discriminative VQA or classification, the process is totally transformed.
Tell us about that shift.
Instead of generating text, they encode all the candidate labels into their own embeddings, scandidate. The model then treats the problem as a nearest neighbor search.
Ah, okay.
It predicts SY hat from the visual input in the query. Then it just compares the similarity or distance between SY hat and all the candidate embeddings and picks the closest match.
So answer generation is fundamentally converted into a classification problem over the latent space.
That's it. It's a huge conceptual shift for efficiency. You avoid that entire costly autoregressive sampling loop.
Absolutely. And for text-to-video retrieval?
The unified mechanism still holds. You just rank candidate videos by estimating the similarity between their predicted semantic embedding, SY hat, and the encoded textual query. This versatility just underscores the model's generalist nature.
Let's pivot to the quantitative validation, which I think is maybe the most compelling part of the paper. They set up this critical controlled comparison to really isolate the benefit of latent state prediction over token prediction.
And the control group was meticulously constructed. Both VL-JEPA and the classical VLM baseline use the exact same frozen vision encoder, the same data mixture, batch size, and total training iterations.
So what was the key difference?
The prediction mechanism. VL-JEPA used its 0.5 billion parameter predictor for embedding prediction, while the baseline used a full 1 billion parameter LLM for next token prediction with standard cross-entropy loss.
And the performance gap, I mean, if you look at figure 3 in the paper, it highlights a massive win for embedding supervision in terms of sample efficiency.
It's not a small win. It's a steep climb for JEPA. Looking at zero-shot video captioning, VL-JEPA's performance curve is just far steeper. It shows much faster convergence.
Right.
After only 15 million samples seen, the difference is dramatic. VL-JEPA hit a 14.8 CIDR score, while the token generative baseline only reached 7.1. And similarly, in video classification, VL-JEPA achieved 41.0% top 5 accuracy versus the baseline's 27.2%. So this confirms that latent space supervision is superior for both sample efficiency and absolute performance, even when you're running on a prediction head with half the parameters.
And the efficiency story continues right into inference, which is so critical for real-time monitoring. The architectural decoupling is what makes this possible.
Correct. For streaming video, you want minimum latency. VL-JEPA separates the swift, necessary steps query embedding, which is about 16 milliseconds, and the encoder predictor steps, 126 milliseconds, from the huge cost of text decoding, which is over 200 milliseconds.
So what does that mean in practice?
It means the model can continuously process video frames and output a semantic stream, SY hat, at high frequency, allowing for immediate monitoring or retrieval tasks without constantly having to engage that slow, autoregressive text decoder.
And this capability sets the stage for the true inference game changer, selective decoding. We're only decoding text when the semantics actually change.
Yes. The system works by just monitoring that continuous stream of predicted embeddings. Text decoding is only triggered when the model detects a significant semantic shift, a high variance or a cluster change detected through agglomerative clustering within a local window.
It's like a security guard monitoring a bank vault feed.
That's a great analogy.
The guard doesn't write down the vault is still there every single second. They only write an entry when an actual change of semantic event occurs.
That analogy makes the real-world application perfectly clear. You are dramatically reducing the false alarm rate, or in this case, the unnecessary decoding rate.
So what were the empirical gains in that scenario?
On the EGO-X40 benchmark, selective decoding provided a Pareto improvement. To get the same quality level as uniform decoding at 1 Hz, VL-JEPA only needed to decode at 0.35 Hz.
That's a direct reduction in the number of decoding operations by approximately 2.85 times.
Right, all while maintaining the semantic quality of the output. For video applications where power and latency are paramount, this is a revolutionary operational gain.
Let's transition to the model's overall standing against other foundational models. We can start with the VL-JEPA-based results post-pre-training, focusing on zero-shot classification and retrieval.
Right. So VL-JEPA-based, the 1.6 billion parameter model, showcased remarkable zero-shot transfer. It achieved a higher average accuracy of 46.4% and a higher average recall at 1 of 58.4% across 8 classification and 8 retrieval datasets.
And that definitively surpassed the best baseline, PE Core G, which is a larger 2.3 billion parameter model.
It did. And it showed particular strength on benchmarks that require motion understanding, like SSV2, EK100, and EGO-X40.
That motion-centric strength strongly suggests that the JEPA prediction objective is just superior at aligning visual representations of dynamics and temporal change with language.
I think that's a fair conclusion. And once supervised fine-tuning is applied, VL-JEPA really proves its generalist abilities in visual question answering.
So given its moderate size, 1.6 billion parameters, how does it actually compete with these established, much larger VLM families?
It holds its own extremely well. VL-JEPA achieved comparable performance to models like Instruct BLA and QuenVL on major VQA datasets, GQA, TallyQA, PILP, PalBIF2.
And that's especially when using that discriminative VQA approach, the nearest embedding match.
Yes, that's where it really shines. But the most striking result, the one that really validates the quality of the latent representation, is this state-of-the-art performance in the world prediction task.
That result is a strong technical signal.
It really is. On the world prediction WM task, which requires the model to identify the unseen action that logically explains a state transition between 2 images, VL-JEPA achieved a staggering 65.7% accuracy.
Which is a new state-of-the-art.
A new SOTA, substantially outperforming comparable and even much larger frontier models, including some closed-source ones like GPT-4o and Gemini 2.0. It just demonstrates this superior ability of the JEPA framework to handle abstract causal reasoning in the video language domain.
The quality of the learned representations is paramount, so we do need to briefly highlight the evaluation of the Y encoder itself. I mean, if that component is flawed, the whole premise falls apart.
Right, and the authors specifically evaluated this. They used unimodal text-only evaluation on hard negative benchmarks like Shukor and VSLA.
And the results.
The results show that the VL-JEPA-based Y encoder is significantly more resilient to textual hard negatives compared to PClip, SIGLIB2, and PE Core. This confirms that JEPA training objective successfully fosters this robust, higher quality semantic representation learning within the text component,
resulting in that powerful clustering effect that we need.
Exactly.
Okay, to wrap up the empirical review, let's just distill the 2 most important architectural takeaways from their ablation studies.
First, the importance of the 2-stage training is absolute. Pre-training is non-negotiable. Classification and retrieval performance just dropped drastically by over 17 points when the model skipped that large-scale pre-training stage.
Okay, so that's number 1. What's number 2?
Second, the choice of loss function is critical. The InfoNC loss consistently outperforms simpler choices like cosine, L1, and L2 losses across all the tasks. And critically, it proved necessary to provide that anti-collapse regularization that you need when the Y encoder is unfrozen and trained jointly with the predictor.
That brings us to the conclusion of this deep dive. I mean, VL-JEPA represents a critical and extremely efficient pivot in how we approach vision language alignment.
Absolutely. The contributions are clear. They've introduced a unified, non-generative model that's capable of handling generation, classification, and retrieval. And they've proven superior learning efficiency via supervision in that latent semantic embedding space.
And that efficiency, combined with the native support for highly practical concepts like selective decoding, makes it uniquely suited for these real-time monitoring and streaming applications that were previously just bottlenecked by latency.
Completely.
So what is this foundational shift, the success in aligning vision and text in a compact, shared, latent space? What does it mean for the roadmap ahead?
Well, while this paper focuses on efficiency and generalist capabilities, I think the proven quality of this unified multimodal latent space is the key takeaway for the community. This architecture serves as an ideal and very efficient foundation for future work on advanced multimodal latent space reasoning.
And where do you see that going?
The next logical, and I think highly provocative step, would be developing novel visual chain of thought methods. The potential here is that complex, multi-step reasoning processes could occur entirely within this abstract, compact embedding space, bypassing the slow, costly requirement of generating discrete, token-based self-correction sequences.
So reasoning in the latent space itself.
Exactly. That transition from text-based reasoning to continuous latent space reasoning, that's the future that this paper has helped unlock.